Hello, welcome to demo lecture of the course Deep Learning. Today we will explain and discuss about comparing various optimization techniques. We will basically briefly compare various optimization techniques. But before starting it, we will briefly understand what is optimization and why do we need it in deep learning. We will not go into detail of each and every optimization algorithms into detail. We will just try to highlight what is the key differences between all of them. So let's first start with the introduction. In deep learning, we have the concept of loss, which tells us how poorly the model is performing at that current instant. Okay. Now we need to use the loss to train our network so that it performs better. We keep track of it. Essentially, what we need to do is to take the loss and try to minimize it. We want the loss to be as minimum as it can be, because a lower loss means our model is going to perform better. Okay, it is properly fitting it to our data set. The process of minimizing or maximizing a mathematical expression is called as optimization. Whenever we try to minimize or maximize any particular operations or expression or variables, then it is called as optimization. Optimizers are algorithms or methods used to change the attributes of the neural networks such as weights and learning rate to reduce the losses. Optimizers are used to solve optimization problems by minimizing the functions. We will compare below listed type of optimizer, but we will not go into detail of each and every one. We will just compare which performs what way, what are the limitations of each and every algorithm, and how the next succeeding algorithm tries to resolve it. So let's start it with the first gradient descent algorithm. So gradient descent is basically most basic and most used. It is used in backpropagation, depends on the first order derivative of the loss function. It is a first order derivative loss function kind of optimization algorithm, and the key formula is theta is equals to theta minus alpha into del of j theta. The advantages of gradient descent is it is easy to compute, easy to implement, and easy to understand. The disadvantages are may trap at local minima, it may stuck on local minima, weights are changed after calculating the gradient on a whole data set. Okay, so if the data set is too large, then it may take years to converge the minima. So we will update the parameters only after covering through whole the data set, and this might be a problem with huge data sets. Requires large memory to calculate the gradient on the whole data set, because whenever we are calculating gradient, we need to store the immediate temporary values, which requires large memory. So the next algorithm is stochastic gradient descent, and we call it as STD insert sometimes. An attempt to solve the slow convergence of a simple gradient descent, because gradient descent used to converge slowly. So we tried to solve this issue and named that algorithm as stochastic gradient descent. The loss calculation and parameter update after every training observation instead of whole batch. Okay, instead of going through whole data set and thereafter updating the parameter, now we are doing parameter update at each and every point, at each and every sample. For example, if we have 1000 rows of data, then we update parameters after each and every row, that is in 1000 times for one single data set. So the equation now gets changed to theta is equals to theta minus alpha into del of j. Theta was in simple gradient descent, theta minus theta into alpha into j, alpha into del of j theta. Now we replace j of theta with j of theta comma xi comma yi, where xi and yi are training examples. Here is a rough illustration of how gradient descent performs and how stochastic gradient descent performs. This is gradient descent and this is stochastic gradient descent, and you can clearly basically highlight or see the difference that it goes slowly but goes directly into that direction, while it may fluctuate but may reach faster. So the advantages are frequent updates of the model parameter, and hence converges in less time. Okay, it converges in less time because it is quick, requires less memory, as no need to store values of loss function. Okay, we are calculating each and every parameter update after each and every data point. We are not going through whole data set, then we are not storing it, and hence requires less memory. May get new minimas. It may cover new minimas because it is exploring the space. You can see it. And the disadvantages of STD are, it has high variance. You can see clearly from the illustration. It may suit even after achieving the global minima because it is quite random in nature. Okay, because we are updating or calculating the parameters after each and every data point. To get the same convergence as gradient descent needs to be slowly reduce the value of the learning rate. To get the same convergence as gradient descent, we need to slowly reduce the value of the learning rate. This is one of the disadvantages of this STD algorithm. The third series of optimization algorithm in gradient descent is mini batch stochastic gradient descent, mini batch version of STD. And you can clearly see from the name itself that instead of going to update parameters after each and every data point, we are going to make batches, small size batches, and then we will process it into batch wise batch. An attempt to solve the slow convergence of the simple gradient descent and high variance of the STD, slow convergence of simple gradient descent and high variance of STD. These are the disadvantages of respective algorithms. We try to solve it into mini batch STD. The data set is divided into various batches instead of going through each and every, and after every batch the parameters are updated instead of single data point or instead of going through whole data set. Okay, in a simple gradient descent we were going through whole data set and then updating the parameter, while in stochastic gradient descent STD we are updating it after every point. But we found a trade-off between them, and what we did, we created mini batches and tried to update parameters after each and every mini batch. So now the equation turns to theta is equal to theta minus alpha into del of j theta. Instead of xi yi, we are now replacing them with bi, where bi is the batches of training example. So here we have compared STD with the mini batch. There are a lot of fluctuations because we were updating it after each and every point. Now we created batches. For example, if we have 1000 data points, then we created batches of somewhere around 20 to 50 data points, and after going through 20 or 50 data points, then and only then we are updating the parameters. So the advantages are considered as the base of the gradient descent based algorithms, because we have basically traded off both the disadvantages and came through a solution which works. Frequently updates the model parameters and also has a layers variance. Okay, simple gradient descent wasn't frequently updating the model parameters. Okay, it was updating after going through whole training data set, and also has a layers variance because STD has high variance, so it solved that issue also. Requires medium amount of memory. Okay, not too high, not too low. Okay, STD was not requiring any memory, while simple gradient descent requiring huge memory. Here we found a solution which requires medium amount of memory, which is feasible. All types of gradient descents have some challenges. Okay, choosing an optimum value of the learning rate is a challenge. If the learning rate is too small, then the gradient descent may take ages to converge. Okay, we will learn very slowly. Have a constant learning rate for all the parameters. Okay, all the gradient descent based algorithms have constant parameters. There may be some parameters which may not be want to change at the same rate, so we want different learning rates for various parameters. May get trapped at local minima. These are the disadvantage of gradient descent, because we are basically following the descent gradient based approach, so it might happen. The fourth algorithm in that series is STD with momentum. Let's see, we added a term momentum over here. What is it? Another attempt to solve the high variance of STD. STD had high variance, so we solved it using by creating batches in mini batch STD. The another approach is created, that is STD with momentum. One new hyperparameter, that is momentum gamma, is introduced. It accepts the convergence towards the relative direction and reduces fluctuation to the relevant direction. So it basically tries to provide momentum to the data point. So it converges toward the relevant direction and reduces fluctuation to the relevant direction. The formula is Vt is equal to gamma into V of t minus 1 plus alpha into del of j theta, where theta is equal to theta minus V of t. Here we were doing theta based update. Now we have taken theta also, but the main equation is based on momentum. Vt is equal to gamma into Vt minus 1 into alpha into del of j theta. Here is side by side rough comparison of STD without momentum and STD with momentum. You can see STD without momentum is having very huge variance, while it got reduced into STD with momentum. So the advantages are reduces the oscillations and high variance of the parameters, as we have already discussed and seen into this demo. Converges faster than the gradient descent because it has low fluctuations and hence converges faster. While the disadvantages are, one more hyperparameter is added which needs to be selected manually and accurately. So this is a pain. If the momentum is too high, then the algorithm may miss the local minimum and may continue to rise up. Okay, if we are basically trying to reach the global minima faster and faster, then it might happen that it may just shoot up the minima and try to find it somewhere. The next algorithm in the series is Nastrev accelerated gradient, which we call it as NAG sometime, invented to solve the issue of missing local minima, the issue that was there into STD with momentum. We are trying to solve it now when momentum is too high in case of momentum based algorithm. Okay, this issue was when momentum is too high. In energy NAG, we will calculate cost based on the future parameter rather than the current one. Okay, we are trying to calculate the future position, and we are now trying to take it into account while calculating the current parameters. We will be using gamma into V of t minus 1 for modifying the various weights. So theta minus gamma into V of t minus 1 approximately tells us the future location. It looks ahead method. It is look ahead method. Okay, we are trying to look ahead what is going to coming up. So the formula changes to something like this. The earlier formula was Vt is equals to gamma Vt minus 1 into alpha del j theta. Okay, where theta is equals to theta minus V of t. Now the updated formula is theta remains the same, but Vt is equal to gamma into V of t minus 1 plus alpha into del of j theta was there here. Now instead of j theta, we have taken j of theta minus gamma into V of t minus 1. Okay, this particular term instead of theta. So this will help us predict the future and take the corrective action right at this step. So the advantages are, it does not miss the local minima, slows if the minimas are occurring. If minimas are occurring, it slows down. Disadvantages are, still the hyperparameters need to be selected manually. Okay, still we have few hyperparameters. The increased one, momentum. So the next algorithm is adaptive gradient. We call it as ADAGRADE in short. An attempt to solve the problem of tuning learning rate manually. Okay, the only disadvantage that we discussed in the last previous algorithm is still a lot of hyperparameters that need to be selected manually and tuned manually. So this is the attempt to solve this problem. In ADA grade, we change the learning rate eta for each parameter at every time step t. So we are now tuning eta from each and every time step t. Eta is learning rate which is modified for given parameter theta I at given time based on the previous gradients calculated for given parameter. For each and every parameter, we are now automatically calculating the learning rate and updating it. We store the sum of the square of gradients with respect to theta I up to time step t. From beginning to the time step t, we are saving the sum of the squares of gradients, while epsilon is smoothing term that avoids the division by 0. Okay, it makes sure that we are not dividing by 0. It makes big updates for less frequent parameters and small steps for frequent parameters. So it is changing learning rates. The formulas are given below. Let's go to the advantages. The learning rate changes for each training parameter. So for each and every training parameter, we are automatically calculate the learning rate, which is dynamically changed after each and every data points. So don't need to manually tune the learning rate. Able to train on sparse data. If we have sparse data, then it is working solution for that too. While the disadvantages are computationally very expensive, as needed to calculate the second order derivative for updating the learning rate. The learning rate is always decreasing, resulting in slow training. So this is the biggest issue with this particular algorithm, that over the time eventually your learning rate will become 0 and learning will stop. Now the next algorithm is ADA delta. It is an extension of ADA grade which stands to remove the decaying learning rate problem. The problem that we discussed last, okay, that the learning rate of ADA grade decays and then ultimately limits to 0. Instead of accumulating all the previous squared sums, that is what we were doing over here, that we are storing the sum of the squared up to time step t from the beginning. Instead of that, what ADA delta does, it limits the window of accumulated past gradients to some fixed size w. So it puts a limit w that we are going to store this w weights parameters only, okay, not since the beginning. So in this, exponential moving average is used rather than the sum of all the gradients. So we are basically now trying to exponentially moving average. The concept of moving average is key here. So here are the equation to update the parameters, and the advantages are now the learning rates does not decay and training does not stop, which is huge, and disadvantages still computationally extensive. Okay. RMS prop, we are not going to discuss it in detail. Let's see it in short. RMS prop is a fact, in fact is identical to first update vector of ADA delta that we derived, one of the version of ADA delta. RMS prop also well divides the learning rate by exponentially decaying average of the sum squared gradients. Hinton suggests gamma to be set to 0.9, while good default values should be eta is equal to this. And the key formula is this: RMS prop and ADA delta have both been developed independently around the same timing from the need of resolving ADA grades radically diminishing learning rates. So it is basically nothing but one more attempt to solve the issue of ADA grade. One of the possible is ADA delta and the second is RMS prop. Okay, having slightly different approach, they both do the same thing. The next is adaptive moment estimation, and we call it as ADAM algorithm in short. Adaptive moment estimation works with the momentums of the first and second order. In addition to storing the exponential decaying average of the past squared gradients like ADA delta, ADAM also keeps track of first moment and second moment. First moment is mean of the past gradient MT, and second moment is uncentered variance of the gradients. So mean and variance, it stores both and keeps track of them, while in ADA delta we were basically doing exponentially decaying average of the past squared gradients only. Okay, here we are taking care of means of gradient and variance of gradient. We are taking care of both of them instead of just gradients. So here are the formulas for mean and variance, and this is the parameter update formula. The advantages are the method is too fast and converges rapidly, one of the best solutions till now. It rectifies the vanishing learning rate and high variance, both of them. And the disadvantage is only one, it is computationally costly. Here is a rough geometry, you can see illustration GIF, where we have compared STD, momentum, nag, ADA grade, ADA delta and RMS prob. The illustration for Adam is not yet available. So let's see and derive the conclusion here. Now, observing the above animation, theory, we can draw following points. The first point is, it is observed that STD algorithm, there is this red line stuck at saddle point. Okay, here is the saddle point. It gets stuck to saddle point. So STD algorithm can only be used for shallow networks. If the networks are shallow, then you can use it. All the other algorithms except STD finally converges on one after the other, ADA delta being the fastest, followed by momentum algorithm. So ADA delta, that is this particular color, is fastest. ADA grade and ADA delta algorithm can be used for sparse data. For sparse data, we have two options, ADA grade and ADA delta. Momentum and nags works well for most cases, but it is slower. Okay, momentum and energy works for anything, but it is slower. Animation of Adam is not available, but from the plot above, it is observed that it is fastest algorithm to converge to the local minima. And the last and verdict point is, Adam is considered the best algorithm amongst all the algorithms discussed above. So that was it in today's lecture. We tried to basically made a summary or made a comparison, quick comparison between all the different kind of optimization algorithms and what are the limitation of each of the algorithm and how the next coming algorithm tried to solve it. So that was it. Thank you.